Okay, hello guys, how are you? I hope it's all been okay. And what we have actually doing, you already know by our approach towards video, is just to actually get ourselves and also our viewers just an awareness about aerospace, aerodynamics, and the related concepts when we actually take a flight. So, what are the components? What are the dominating factors? What are the aerodynamic properties and forces? What are the estimations that may help us to just come across the result which is according to the standards or the standard conditions in which actually we assume that the flight has been taking off or it's been landing. So we're just going to take just from the same concept of the approach, we're going to implement a test method just to estimation of the yaw moment coefficient, which is Cn of beta. And in the previous video we talked about what is rolling moment equation, which was Cl into Cl of P, Pb 2V of T plus Cl of R, Rb into 2 divided by 2V of T plus Cl beta into beta plus C L lambda A into lambda A plus Cl lambda R into lambda R. That was for the rolling moment, and that is why we just took that equation. And the main part was after Cl, which is Cl of beta into B over 2V of Vt plus Cl Rb into 2 into Vt, which is the third part, that is Cl of beta into beta. Okay, the Cl of beta was the rolling moment, and that is why we have to have that one, Cl of beta. Okay, so that one, also the derivative was also Cl of beta, and then we actually replace the same equation with the Cn instead of L, and we have actually now Cn, you can see in which is a Yawing moment equation. And over here with what we have to find, which is this one, Cn of beta, okay, which is the rolling or the yawing moment coefficient. And the Cl of beta is what is the rolling moment coefficient, which we're going to actually estimate in our next video. But what we actually learned from this equation was the rolling moment derivative, which was this Cl of R. Okay, so that we took as a derivative and we calculated as Cl of R by our further equations and further simplifications and assumptions in one of the previous videos. But obviously in our next video we're going to see Cl of beta, which will be rolling moment coefficient. Okay, we have actually calculated side slip coefficient, which is, if we're going to actually replace this with Cy instead of Cl or Cn, we just going to say it is Cy, because side slip is normally in directional of nature or in the vertical direction. So Cy would be placed, because of that it would be Cy beta of beta, and then Cy beta would be called as side slip coefficient, which we have calculated in our previous video. So just keeping in track of the same approach, we're going to calculate what, with the help of the Yawing moment coefficient, Yawing moment, which is this, we're going to calculate Cn of beta, which is now the Yawing or the yaw moment coefficient. Okay, you just have to keep that in mind. The same equation is being replaced by different symbols according to the nature of the component, and also in nature of the force. Whenever there is a roll, there is also a yaw. Whenever there is a roll and yaw, we have to find there will be equation of motions, there will be coefficient involved, and also when there is a coefficient, we talk about the side slip coefficient as well, when there is beta is equal to 0, and also when there is side slip coefficient, we want to have phi as well, we want to have beta as well, we want to have theta. These are the assumptions which are the control angles. And naturally we are just dealing with the coefficients. We are dealing, the coefficients are normally calculated with the help of the estimation and also with the help of the derivatives. Okay, so the whole concept is just surrounded by aerodynamic properties, aerodynamic components, aerodynamic forces, which make up all the components to actually get the flight test completed, and also according to the standard conditions. So naturally we have to follow some basic steps, and after our assumptions are absolutely right, whether it is applied to any component, whether it is applied to any derivative, whether it is applied to any coefficient, we can say that our flight test, or even eventually flight and on regular basis, is absolutely right and okay as per the standard conditions, as per the standards required. For a steady state side slip, which is obviously static case, and Cn is equal to 0, P is equal to 0, R is equal to 0, Cn beta into beta, Cn lambda A into lambda A plus Cn lambda R into lambda R is equal to 0. This equation shows that the rudder is required to counteract the weathercock stability Cn of beta, and the aileron yaw, which is Cn of lambda A. Okay, so this is lambda A's aileron, because aileron component, okay, or the aileron coefficient you can say, and Cn lambda R is because of rudder. But we have to calculate Cn of beta, which is yaw, okay, and that is for the steady slip. These all conditions are calculating the coefficient, and coefficient one is related to the steady slip. We have actually calculated our calculation mainly, if you're talking about from the steady state coordinated turn. Obviously what we have calculated the coefficient because of that steady state type, and because of steady state normally that revolves around beta, and also all the coefficient will also be around that. That is why we have calculated this one. But obviously aileron A and because of the rudder, these can be calculated separately but not under the same which is the paradigm. These factor will obviously add on, but the major part would be around this Cn of beta. These are the compensating factors, not actually the major part, but obviously they compensate which is Cn of beta, cock stability, and the aileron, and Cn lambda R. It may be noted that the value of Cn lambda okay, can be estimated using recorded values of lambda A, which is lambda A and lambda and beta, lambda A, lambda and beta, provided the values of Cn lambda A and Cn lambda R are known a priori. Okay, so further, if we know the value Cn lambda A and Cn lambda R, okay, and by the recorded values of lambda A and lambda R, lambda A and lambda R, and eventually of beta, okay, we can estimate the relationship, or we can actually then we can show that beta over lambda R is equal to Cn lambda R over Cn of beta. That is our actually main part that needs to be calculated. Actually, where Cn lambda R is negative and Cn beta is positive, so definition for a stable airplane. Okay, so Cn beta will always be positive, but Cn lambda R, because of the rudder, the rudder, that would be of a negative. So that is the equation derived. Thus, for an aircraft having directional stability, okay, what we are talking about? They were talking about the directional stability, because there is a yaw moment, there is a yaw moment coefficient, there is a yaw moment component. We have already gone through the whole concept. The slope of plot of beta versus lambda R will be positive. We have to calculate, obviously, because of beta and also the lambda R, we need to calculate the relationship between these two. So flight test to estimate estimate yawing moment coefficient Cn of beta. Record the takeoff weight of aircraft. First of all, you have to record the takeoff weight, and note down the velocity v, altitude h, rudder deflection lambda r, and angle of side slip beta during the steady side slip maneuver. We are actually doing this under the steady side slip maneuver. That is the condition, and all these coefficients are calculated for that steady side slip, so that we can say that the turn is absolutely right. Now given c and lambda r, other derivative c and beta can be estimated with the help of the expression. We have calculated this. Plot beta versus lambda. We'll find the slope of plot will be positive. Absolutely right. So I can draw it right now, but you can draw it by yourself. If there are any problems, we can actually discuss in our next video or in the coming videos, that we can actually draw a plot, a graph as well, just to show the relationship between beta and lambda r, and the slope would be positive. And note, since c and lambda r is negative, we have shown by the equation, because of the rudder, c and beta is always positive, so the relationship between cn lambda r into cn of beta is positive. Okay, because the denominating factor would be here, we have to calculate cn of beta, so that the whole equation would be, the result would be, needs to be positive. So that is all together this video. And how obviously what we have estimated is the yawing moment coefficient, and because of the yaw moment is actually being counteracted by what? It's been counteracted by the rudder, and also obviously rudder is required to counteract this cn of beta, and also with cn of lambda a, which is the stability because of the aileron. So that is why the main component would be because of a rudder, and rudder is all at the vertical position at the tail, and normally because of that we have the yaw coefficient, and that is how it has been counteracted. So we have calculated that it is the test method is obviously for the dominating factors, which are the lateral and directional stability. So the dominating factors would be cn of beta and cn of lambda a, because of the side slip. Obviously beta is an essential, and obviously we can say that the control angle and the aileron stability are the major factors or the dominating factors, and the rudder is actually counteracting these two just to create or balance off the stability or the instability in case of this, if it's stronger. But the dominating factors over here we are talking about in terms of lateral and directional stability, and in this case we have talked about the directional stability, and side slip coefficient is being covered, and which was by that equation which we have derived for Fy, and we have actually added on the weight factor as well. That was for the side slip, and afterwards we have calculated the yaw moment coefficient as well, and in the next video we're going to calculate the rolling moment coefficient, and or estimation of the rolling moment coefficient. So that will actually help us to get all the components in line. Okay, but obviously all the components will revolve around this one, the third part. If you're going to replace it CL of beta, Cy of beta, that would be what? The side slip coefficient. If it will be Cl of beta, that I have talked earlier, that would be rolling moment coefficient, and Cn of beta, that would be the yaw moment coefficient. Okay, so these two, aileron and rudder, will play the part. Okay, for as far as the directional stability is concerned, and let's see in the next video how these factors or the components will play as far as the rolling moment coefficient is concerned, and obviously that would be under the paradigm of the lateral stability, and when we're talking about the steady side slip maneuver, okay, where beta is equal to 0, and also the other assumptions that we have taken as far as the lambda r, velocity by the airspeed indicator, and altitude is also measured by the instrument. We may actually draw some of the graph as well, I believe, in some of the incoming videos, just to actually clarify ourselves and what are the different sort of the instruments. But we're also going to give another video, or just provide you another video in which we're going to discuss the terminologies and the definitions. If you are interested in getting the terminologies and definitions related to the aerodynamics, the aircraft, related to the aircraft structure, we'll just provide a separate video. But with the passage of time, we are just dealing with the concepts, that is the numerical concepts, the estimation, that is the major part. As far as the engineering perspective is concerned, we need to be very sound, we need to be crystal clear in terms of engineering of the aircraft design, aircraft maneuvering, and aircraft stability. The factors that are from the engineer's point of view, that is of importance, and we're going to actually handle those. And also our videos are basically meant to serve the engineer's perspective, and also whether it is with the help of theoretical approach, whether it is with the help of you can say a thematic approach, or with the help of algebraic expressions, or with the help of theoretical explanation, algebraic expression, arithmetic calculation, or with the help of graphical representation, which in terms of plot, whether in terms of estimation, whether we use some software, normally it would be MATLAB or something that may actually, or likewise, that may help us to actually just show what was the basic theme of our, how you can actually estimate or plot, because that is why I've actually not shown some plot this way. We will actually calculate or show you the plot in real time, obviously by examples as well, so that you can get an idea what is the real purpose of graph and what is the real purpose of using some softwares that help us to understand the engineering perspective of aircraft, engineering perspective of aerodynamics. So I hope that I have actually explained just in terms of estimation, and I've given you the idea that how we're going to approach. But yet again, I'll also recommend that you do subscribe, like, share as well. Along the line, you just visit our videos for our other services that we actually do offer, and if someone is interested, we can coordinate and we can negotiate on some suitable and best terms on both sides. So hope to see you with our next video. Till then, take care and have a nice day.